So, very good evening, everyone. Today, we will be discussing about the rubber industry, which will be the last topic of this syllabus of organic chemical technology. So, mm, we will be discussing thoroughly about the rubber industry. There are various rubbers that is available, but for the production point of view and the point of view of flowchart and describing the whole procedure, we'll be focusing on the two majorly used polymers or rubbers. So let's begin with the presentation for today. First, we will quickly go through the introduction part that will give you the brief overview of the rubber, origin of rubber, and the uses of rubber and other variety of rubbers, right? So, for your information, it is written that India is the fifth largest natural rubber producing country in the world. This natural rubber which is collected from this tree, that is Hevia brasiliensis. They belong to the family Euphorbiaceae. Euphorbiaceae, right? Now from this tree, we generally collect the latex from this tree, and we form the natural rubber out of that. Now this Hevia brasiliensis, this species, they produce 99% of the world's natural rubber, and its yield and quality of the latex is superior over other species. This latex is nothing but a colloidal dispersion of some solid particles of the polymers, which is polymer is known as polyisoprene, dispersed in the water. That forms a colloidal, that is called latex. Now this natural rubber is the polymer form of the isomer isoprene. So it forms polyisoprene, which is a chemical substance that comprises of the rubber, and its content in the emulsion is about 30%. So this polyisoprene polymer percentage is 30% when it is dispersed in the water solvent, you can say. The natural rubber or the polyisoprene has very high elasticity, high resilience, and high tensile strength. The synthetic rubber, on the other hand, that is produced from the petroleum feedstock through polymerization or polycondensation reaction. Now the naphtha, which is produced during the petroleum refining process that we have discussed earlier, that is being extracted and then mixed with the natural gas to create some monomers out of that, like styrene or isoprene. This kind of monomers are derived from naphtha origin, and from these monomers, using these monomers of styrene and isoprene, we manufacture synthetic rubber. A benefit of the natural rubber over the synthetic rubber is that natural rubber, they have very high tensile strength, higher resistance, tear resistance, and low odor compared to the synthetic rubber. Furthermore, These synthetic rubbers can have excellent heat resistance and lower temperature resistance, and also improving heat edging property. So these are some differentiation between natural rubber over synthetic rubber. After this quick introduction of the rubber industry, we will proceed with the preparation of natural rubber. See, this natural rubber, the source is some tree. The tree is Hevia brasiliensis. From that tree, we collect the latex and we process to make rubber out of that. So we are going to discuss what is the preparation method for producing natural rubber. The latex sap of the rubber tree is used to make the natural rubber. The latex is harvested by affixing a container to the rubber tree, which is referred to as tapping process. After the tapping process, or after the latex is being collected, the formic acid is used as a coagulating agent. Those are introduced into the latex for coagulation, and they become a hard mass as a result of this coagulation process. This rubber, natural rubber, they completely dried after that, or either with a series of roller, or by allowing them by simply air drying for several days. These natural rubbers, now such way they are ready for the processing and will be used in for making variety of products. So for your example, suppose you have uh, those polyisoprene, those are naturally occurring. We don't have to do the polymerization. Those are naturally occurring polymers. I'm giving you the structure of the isoprene. So this is isoprene. So after polymerization reaction, it forms polyisoprene. So how it forms, this is the repeating unit I am going to write. It forms CH2. So from this end, it will go on. Also from this end, it will go on. Other things will be same. N number of this repeating unit will be there. This is known as polyisoprene, also natural rubber. Next we will discuss about the processing of rubber. So processing of rubber, it has four processes, or you can say four steps. After the coagulation of the rubber from the latex, we need to do some processing to make it useful for the rest of the product making steps. So the four steps are compounding, mixing, shaping, vulcanizing. Coming into details, compounding is to make the rubber is fortified with additives and chemicals to improve its tensile strength and other characteristics. So for this, we are adding carbon black fillers to make the rubber tensile strength, having more tensile strength, and protect it from the ultraviolet radiations from degradation. There are other compounding agents also we will discuss in the further slides. Next step is the mixing. Then rubber must be well mixed with the additives before use. The temperature is raised for in the mixing stage and the additives are thoroughly blended by this mixing. Shaping, extrusion, calendering, molding, coating or casting. These are four common methods for shaping the rubber items. Extruders, they force a highly plastic rubber through a series of screw extruder to create rubbers. Calendering follows this phase, which involves passing the rubber through a series of smaller gaps between the roll. This roller die method combines extrusions and calendering to create a superior result out of that. This coating is the application of rubber coat or the pushing of rubber into the cloth or other material. Rubber coating are used to make tires, waterproof textile tents, raincoats, conveyor belts and other items. Molds, which are used to make rubber products as a shoe sole, heel seal, suction cups and bottle stops. Last method is vulcanization, which is important. We will focus more in the upcoming slide. Vulcanization is the process where rubber processing finished. It finished with the vulcanization, where sulfur is added for making the cross connections between the rubber polymers to give it more strength. Rubber that has very fewer cross connections between its polymer are often softer. The elasticity of the rubber is reduced as the number of cross connections increases. It becomes more hard, the elasticity reduced, resulting in a harder rubber. Rubber would be sticky when hot and brittle when cold if it was not vulcanized properly. So to make it more durable, vulcanization process is highly recommended as a last step of rubber processing. Next we will discuss about some monomers and polymers or copolymers of the rubbers. So you can see the isoprene, which is also known as the monomer of the natural rubber. It forms the polymer, which is polyisoprene, and it has this kind of structure that we have discussed in the previous slide. Next one is butadiene monomer. It forms the polybutadiene um, polymer. So it forms from this end here, it is making polymer. This will add these are some repeating units. These will repeat further. Same thing will repeat further. Chloroprene, it forms polychloroprene, also known as neoprene. It has CH2, C11C. Here the chlorine group is present. That's why it is chloroprene. And this is the repeating unit for polychloroprene. Now we will discuss some copolymer. For making the SBR, the copolymer is styrene and butadiene. Sorry, the monomers are styrene and butadiene. It forms styrene butadiene rubber or SBR, also known as Bona S. This is the trade name. So in this structure of SBR, you can see this part is butadiene and this part is the styrene. And this M and N, this has separate numbers, and this will form the polymerization reaction. This will form the polymers by connecting same repeating units in the both end. So as we can't say that this is a whole n number of units will um, be repeating based upon the uh, weight percentage of the monomers are added for producing the SBR. This M and N, these two value will be different or will vary. Another copolymer is NBR or nitrile butadiene rubber. It has monomers, two monomers, acrylonitrile, and another one is butadiene. So this unit, this one is acrylonitrile and this one is butadiene, right? Again, this is M and N. So these two depends on the in how much proportions you are adding while making the NBR. Another one copolymer is the ethylene propylene diene monomer. For these, the monomers are ethylene and propylene. So it has this kind of structure while X, Y, Z, three changing units can be there, and this whole unit is these are connected between one, and from this end it will go repeating pattern. Some other um, copolymer is butyl rubber. The monomers are isobutylene and isoprene. So from this end it will go on repeating, where n is the repeating number. Next one is the ethylene vinyl acetate, which is known as EVA. It has three monomers like ethylene, vinyl acetate, and acrylonitrile. It forms this kind of structure of repeating unit. Next one is the thiocol, or which is also known as polysulfide rubber. It has monomers of ethylene dichloride and sodium polysulfide. It has simple repeating unit like this. So it will go on, right? Next, we will quickly discuss on the classifications of the rubber. First one is elastomers. So, elastomers are categorized like vulcanizable. Among that, dyne rubbers or dyne elastomers, those are derived from dyne monomers. Dyne monomers means it will have uh, two double bonds in their molecular structure, and those possesses considerable degree of unsaturations. So it has unsaturations, and it can be vulcanized and very much vulnerable to oxidation and ozone attack. Examples of this dyne rubber which can be vulcanized, those are polybutadiene rubber, styrene butadiene rubber, polyisoprene rubber, that is natural rubber, nitrile butadiene rubber, chloroprene rubber. The other non-dyne rubbers which can also be vulcanized, those are derived from monomers which do not contain the dyne monomers, typically which are more resistant to the oxidation and more resistance to the weathering than the dyne rubbers. Examples are butyl rubber, acrylonitrile butadiene rubber, styrene butadiene rubber, this will be discussed further, ethylene propylene dyne monomers, chloroprene rubber, and hydrogenated nitrile rubber. Next category is non-vulcanizable and other elastomers. Those have some category. So class 1 is elastomer, class 2 is hard plastics, class 3 are reinforcing resins, and class 4 are paint vehicles. Some classifications of rubber. We will now discuss how the production of synthetic rubbers are happening. Natural rubber, those are originally placed in nature as a polymer. But for the synthetic rubber, we need to go through some polymerization method to make the polymer from the monomers. It can be one kind of monomer, or it can be multiple addition of monomers. So the production of the synthetic rubbers, synthetic elastomers are produced on an industrial scale either by the method of solution polymerization or emulsion polymerization. Polymers made in solution generally have more linear molecules, that is, less branching of side chains from the main polymer chain in the solution polymerization, and they have very narrow distributions of the molecular weight and flow more easily, which is produced by solution polymerization. In addition, the placement of the monomer unit in the polymer molecule can be controlled by more precisely when polymerization is conducted in a solution. The monomer or monomers are dissolved in the hydrocarbon solvent, usually used hexane or cyclohexane, and then it is polymerized using a organometallic catalyst such as butyl lithium. In case of the other emulsion polymerization, the monomer is emulsified in water with a soap. That soap can be sodium citrate, which is employed as a surfactant, and a water-soluble free radical catalyst, such as potassium persulfate, peroxide, and a redox system, is then added to induce the polymerization, emulsion polymerization. So after the emulsion polymerization, the reaction is stopped by adding a radical inhibitor. It is added further to stop that polymerization reaction. The 10% of the synthetic elastomer produced through emulsion technique is sold as latex, and rest is coagulated acidified brine, washed, dried, pressed into 35 kg or 77-pound bales, and then it is sold. Okay, mostly the emulsion techniques are used. Next, we will discuss about one of the most important step of the rubber processing, that is vulcanization. So the vulcanization is a chemical process for converting the rubber or related polymers into more durable material via addition of the sulfur or sulfur um, containing compounds. Uh, those are known as curatives. So vulcanization process is also known as curing process. So these additives, they will modify the polymer by forming the cross-linking or bridges between the individual polymer chain under heated condition and pressurized condition. The temperature is maintained above 140 degrees Celsius. The vulcanized material will be less sticky and has superior mechanical properties. For that only the vulcanization is being done. The vulcanization decreases the flow of an elastomer and increases its tensile strength and modulus, but preserves its extensibility. It becomes more harder by vulcanization process. The process of vulcanization can be speeded up considerably and the sulfur waste reduced substantially by the addition of small amounts of organic or inorganic compounds which are known as accelerator. Many accelerators themselves require the presence of activators or promoters. So accelerators are not sufficient sometimes. They also need the dependency of the activators or promoters. Activators are normally some metal oxides such as zinc oxide. There are other activators as well. You have to choose based upon the cases. The use of the accelerator and the activator has increased the efficiency of cross-linking between the individual polymer chains. In some cases, to less than 2 sulfur atoms per crosslink. Now we will see some of the examples of the accelerator. Suppose first example is 2 mercapto benzoethazole thiazole. Benzoethiazole. So this is quite strange name. This structure. One benzene ring is there and nitrogen. This is sulfur atom attached. So this sulfur, presence of this sulfur, it will helpful for vulcanization and helpful as a accelerator. Next one is tetramethyl thiouridisulfide. There two sulfur atoms are present and also in the link there are two sulfur atoms. So this structure is known as, it is also acts as an accelerator. Diphenyl guanidine, this structure represents zinc butyl xanthate, this structure. Some of the properties that will be highlighted here of the vulcanized rubber, those are heat resistance power. So the vulcanized rubber is less likely to melt or soften at high temperature. So these are some advantages. Elasticity: vulcanized rubber maintains its elasticity and flexibility across a wide range of temperature. But that elasticity is reduced than the actual polymer. Solvent resistance: vulcanized rubber swells less when exposed to any kind of solvent or liquid. Tensile strength: vulcanized rubber has increased the tensile strength. Abrasion resistance also, those are increased by this vulcanization process. Resilience: it is resilient and returns to its original shape. Water absorption has low in case of the vulcanized rubber. Electrical insulator: it is a good electrical insulator. All kind of vulcanized rubber. Oxidant resistance: these had high resistance to the any kind of oxidation. So vulcanized rubber is used in many products including tire, gasket seals, conveyor belts and shoe soles. We are discussing about the compounding of rubber. Pure rubber, which is natural or synthetic, those are not suitable for the use. Those should be uh, compounding before the further use of the rubber for making other products out of that. The desirable properties such as plasticity, elasticity, toughness, roughness, and hardness, softness, abrasion resistance, impermeability, those kind of extra characteristics can be achieved by compounding process. So this is the whole lot of compounding agents that we are going to discuss and some of the examples. So first one is the curing or vulcanization process. For that we add sulfur, sulfur monochloride, selenium, polysulfide polymers. Accelerators we add already, we have discussed, to mercaptobenzothiazole, zinc, diethyl dithiocarbamate, tetramethyl mono or tetramethyl disulfides. Accelerator activators are used like metal oxides like zinc and magnesium oxide, steric acid, litharage, amines are used. Retarders to stop the reactions of polymerization, that is salicylic acid, uh, benzoic acid, phthalic anhydride. Antioxidants, those are N-phenyl 2 naphthylamine, alkylated diphenylamine, acetone diphenylamine condensate, those are antioxidants we use. Antiozonates, Those are derivatives of paraphenyl. Fillers are used: carbon black, clays, silica, zinc oxide, calcium carbonate. Softeners or extenders are used: petroleum oils, pine tar and resins, coal tar fractions. Blowing agents are sodium or ammonium bicarbonate, di diazoaminobenzene, fluorocarbons. Chemical plasticizers are 2-naphthalothiol, mixed xylene thiols. Peptizers are aromatic mercaptans or thiophenols. There are other examples. I have just highlighted some of the examples. The next one we will discuss about the production of the foam rubber, which is a very essential part. Those are used widely as a foam rubbers in various applications. So foam rubbers are widely used in the furnitures, mattresses, upholstery, employed in gasket seals and weather stripping. It is also used as a thermal and acoustic insulation in building and vehicles. Also, it is widely used in the sports and safety equipments. So, the foam rubber, flexible, porous substance made from a natural or synthetic latex, compounded with various ingredients and whipped into froth. So, this compounding agent we have discussed in the last slide. The resulting foam rubber contains roughly 80%, 85% of the air and 15% of the rubber and can be molded and vulcanized. In special processes, a blowing agent is also incorporated in the latex to liberate the gas during the vulcanization process, forming small closed cell. The resultant foam is non-absorbent and useful for thermal insulation in the refrigerator. The closed cell foams are the preferred material for thermal insulation, seals and gasket that protects against the moisture and chemicals, UV light or ozone, dynamic shock absorber as well as for the packaging. We use the closed cell foams. Meanwhile, open cell foams are employed in seating, automotive trim, filters and acoustic applications. Next, we will discuss about the production of Buna S, which is also known as butadiene styrene copolymer. It is being called as copolymer because it has two different type of monomers. One is butadiene, another one is styrene. Rubber Buna S is produced by the copolymerization method of butadiene, which is 75% by weight, and styrene, which is 25% by weight. So the butadiene and styrene ratio is B by S ratio is 3 by 1. This ratio is maintained for the production of Bunais. So what are the properties of the Bunais that we achieve by this copolymerization reaction? This synthetic rubber resembles natural rubber in processing characteristics as well as quality of finished product. It more or less resembles of the natural rubber. The properties of the SBR rubber can be modified by varying the temperature of the polymerization. It possesses high abrasion resistance and high load bearing capacity and resilience. And it swells in oil and solvent. What are the uses of production of Bunais? That is mainly used in the manufacture of the car tires. Other uses of this elastomer are floor tiles, shoe soles, gasket, footwear components, different wire and cable insulations, carpet backing and adhesives. So let us now discuss about polymerization of S or SBR. That is, we have the monomer of butadiene, CH2 double one CH, CH double one CH2, and it has styrene, CH2 double one CH, benzene ring it has. So this is n number of, and this is because they should be in ratio, right? 3:1 ratio. This is butadiene and this one is styrene. So by polymerization reaction, it produces polybutadiene co-styrene, that is CH2 double one CH. So this is the structure. You can see that X, it is for the butadiene part, and this is for the styrene part. This is polybutadiene co-styrene. This is SBR or nice that we are forming by copolymerization reaction. So we are talking about this polymerization reaction. This can be happened by two methods. One is uh, already discussed. One is emulsion polymerization, and another one is the solution polymerization. So in case of the emulsion polymerization, this is kind of the radical polymerization, right? And it starts with emulsion incorporating water, monomer and a surfactant or soap. And this process overcomes the difficulty of the heat control and low degree of the polymerization. It overcomes those of the difficulties, and the main product of this emulsion polymerization is we get latex, and it is widely used emulsion polymerization for producing bunais or SBR, and for coagulating latex we use the ionic salts or acid to make the rubber out of the latex form. Next one is another method is solution polymerization, where the monomer are dissolved into the uh, solvent, and also some initiator is added into the solvents. The solvents can be aromatic or aliphatic hydrocarbons, and they are obviously there is lot of heat of polymerization is evolved. So this kind of polymerization is not preferred that much over emulsion polymerization. Discuss about the production method or this flowchart for production of bunais. So at the first step, the butadiene and styrene are mixed with the steam and it is fed to the reactor where caustic conductor by about 20 percentage NaOH is added to purify the monomers here, and then after purification it is passed to a surge tank and then filler. By filler it is then fed to the homogenizer to proper mixing with the activator soap and modifier which is known as compounding agents, which is known as compounding agents. So it should be properly mixed. That's why it is sent through the homogenizer. Then it is sent passed through the refrigeration. So it is optional because refrigeration is used for the cold. It is only used for the cold rubber uh, process making. Otherwise, it can be cut through. This is optional. So then it is sent to the series of reactor where stainless steel reactors are series placed in series about 6 to 12 reactors, and here there is continuous mixing in the stirring kind of reactor. After the reactions where it takes around 5 to 15 hours long time for the polymerization, and then it is sent through the blow down tank where the latex unreacted latex are being separated out. Okay, and then it is sent to the falling film stripper to separate butadiene as a top product which is being recycled, and then the rest of the product is sent to the through the perforated plate stripper. From here the top uh, product styrene is being separated and it can be recycled back. Then the product from this stripper is sent through the some more mixture where the antioxidants are also used. The product is then mixed with the steam, and again here the carbon back filler is used. After proper mixing, it is sent to the coagulator. So from the coagulation process, we will get the rubber separated from the latex, and it is then sent through the vibrating screen. From the vibrating screen, the watery portion and the solid portion will be separated, and it is sent to the re-slurry tank where again it is passed through the vibrating screen to further separation of the rubber from the latex. It is further fed to the vacuum filter for solid liquid separation and then passed through the dryer to form the SBR rubber to baling. So the whole process is same for cold rubber and hot rubber process. For cold rubber, it is being cold to 5 degrees Celsius, and for hot rubber, it is 50 degrees Celsius for hot rubber process. Otherwise, the all process is same. But to inform or to highlight the difference between the cold and hot rubber, the cold rubber is more having more quality than the hot rubber. Otherwise, all the processes are same. Only the refrigeration part is included for as an extra step for making the cold rubber, because we need to reduce the temperature from 50 to 5 degrees Celsius. The next topic is production of the silicon polymer. So it is an inorganic polymer, consists of silicon and oxygen in the main backbone in their structure. The silicon polymers are used as a high temperature rubber and resin coatings. They can be used at a very high temperature, resistance to that. Some of the properties include poor tensile and impact abrasion resistance, show very good hardness property, excellent low temperature flexibility up to minus 85 degrees Celsius. They are non-volatile, extremely stable up to very high temperature, and extremely resistance to oxidation up to 150 degrees Celsius. So it can be used in the um, as a maintaining the temperature for constant temperature source. Excellent thermal stability, that is there up to 150 degrees Celsius. It is easily um, can be stable. Higher ozone and UV ultraviolet resistance than better than other rubbers, and resistance to the aliphatic motor and transmission oil, but naphthenic oil, alkali acid also swells silicon rubber to greater extent. Hydrolysis resistance up to temperature 130 to 140 degrees Celsius, and adhesive and hydrophobic nature. They do not adhere to adhere to ice, which makes them suitable for any kind of refrigerated profiles. And they are very good electrical insulator, better than other rubbers. Much higher liquid and gas permeation rate they offer, and show very good biocompatibility, non-toxic, that's why good biocompatibility. Next one, we will discuss about some grades of silicon. Most of the important grades are dimethyl polysiloxane, methyl phenyl polysiloxane, and copolymers of both of the type of adding some vinyl compound. Just like MQ silicon, that is methyl silicon. These are linear type structure and very negligible to change of its viscosity at a temperature down to minus 85 degrees Celsius. There is no change in the viscosity. Another one is the vinyl methyl silicon, phenyl methyl silicon. So, if I talk about such example of methyl silicon, it is like silicon and oxygen will be in the backbone, and methyl group will be there. So these are the repeating unit. This is MQ silicon. Suppose we are giving example of the vinyl methyl silicon. So there will be methyl group. By name you can think of, and there will be one vinyl group. Next one, we will discuss the reactions which are involved in the production of the silicon. Mostly two steps are there. One is hydrolysis, and next one is the condensation process. So it starts with some monomer, which is um, alkyl or aryl monomers are used, which undergoes the hydrolysis process of the halogen atoms to produce the reactive siloxane intermediates. And that reactive siloxane, those are highly reactive and they further participate into polymerization reaction. So the first step, which is hydrolysis, suppose I give one example general. This is the alkyl or aryl halo silence. Okay, it reacts with water. It forms siloxane. So this A and B, this summation should be maintained 4. And this B denotes the degree of functionality of the monomer. This siloxane is highly reactive. It further processed to the condensation next part, where suppose this siloxane, it forms polymerization and it forms the silicone. So this polymerization reaction should be terminated by addition of some monofunctional trialkyl or monofunctional triaryl monomers to terminate the reaction. The formation of this, it will be terminated. To describe this production flowchart of the silicon polymer, the silicon metals are first crushed into the ball mix and the powdered form is fed to the methylating tower. So this is the methylating tower reactor where there is maintained the cooling jacket to maintain the temperature of the reactions, because this is highly exothermic reactions. Also in the reaction we are adding CO co-catalyst. Temperature is maintained to 50 to 300 degrees Celsius. The mixture is then the mixed methyl chlorosilane are here in this reactor is formed by uh, introducing the methyl chloride vapor into this mixture, and the mixed methyl chlorosilanes are then passed through the series of reactors or the fractionator, where the high boilers are collected from the bottom and the low boiling are sent to the further distillation columns, where we can see that some monomers are separated by these three distillation columns. One is trimethyl chlorosilanes, methyl trichlorosilane, and dimethyl dichlorosilanes. So from there, this trimethyl chlorosilanes and dimethyl dichlorosilane, those are okay. Trimethyl chlorosilane is fed to the this reactor, which is the hydrolysis reactor 1 and hydrolysis reactor 2. Okay, so these two product, these and these two product is sent to the two hydrolysis reactor, where water is added in both of the reactor, and as a byproduct you are getting HCl. So the product is further taken uh, for the neutralization, because there might be XL HCl. So we are adding Na2CO3 in both of the process, that is known as neutralization process, and then further sent to the filters, and you will get Na2S4 salt will be separated out, and after that those will be mixed and sent to the polymerization reaction. Uh, in the reactor we are using H2SO4 as a catalyst, and after that there will be to remove any kind of excess acid, we are again using the neutralization using the Na2CO3. Again it is passed through the filter to separate out the salts. And then after that it is sent through the distillation or fractionator, where the light oils are separated, it can be further recycled, and silicon oils we are getting as a bottom product as a higher density. So this is all for today's class. So we have discussed about rubber technology, discussed about few of the flowcharts. So that's all covered for this today's class, and this will be last lecture. This is the last lecture for this this topic of organic chemical technology, this course, and hopefully I have covered all the lectures and all the topics including the syllabus. And if there is any question, you can comment down below in the YouTube. I can help before your um, actual NPTEL exam. So best wishes for your exam of NPTEL, and hopefully we will meet again for any other NPTEL course in the future. So thank you so much for for being with this all classes online, and wishing you very best for your upcoming NPTEL exam. So thank you. I'm signing off. Good luck.